are very glad that we have Bowen Wen, who is a third-year PhD student in Computer Science Department at Rutgers, to give us this talk on related to robotic arm manipulation. Bowen is working with Professor Costa Burkis. He got his Bachelor of Science degree in Energy and Automation from Xi'an Jiaotong University in 2016, and a master degree in ECE from Ohio State University in 2018. His research interests include robotics, computer vision, and artificial intelligence. He has published papers at ICRA, IROS, Conference on Robotic Learning, etc. He also has a lot of internship experience with great companies like Facebook Reality Lab, Amazon Lab 126, and Samsung. Without wasting more time, I will now invite Bowen to give us a talk. And Bowen, thank you to you and Professor Burkis. Also, thank you for allowing Bowen to give us this talk.
Yeah, thank you, Professor Chua, for this introduction. But also, thank you for inviting, and thanks to Jinda for helping to coordinate this. Hello, everyone. I'm Bowen. Today, I'm going to talk about robust real-time 60-pose estimation and tracking for robotic manipulation. First, let's look at what is the 60-object pose. So suppose we have the CAD model of the target object, and also the RGB or RGB-D data captured by the camera. And we want to find the transformation that brings the object's local coordinate frame into the camera's frame. And this transformation is noted as the 60-pose P, which includes the rotation and the translation term. This pose is in SE3 space. And why is 60-object pose useful in robotic manipulation? Consider some examples as below. Let's first look at the OpenAI dexterous hand. So you guys may have seen this video. In this task, the OpenAI dexterous hand tries to rotate this cuboid to some predefined orientations. So in order to achieve this task, the robot needs to constantly have a knowledge about the rotation of this cuboid, so that it can rotate to the right direction. Also, in the case of logistics packing, when the robot wants to pick and place the objects into a bin, it also needs to have knowledge about this 60 pose of the objects, so that we want to pack these objects densely and aligned in the bin. However, there are some challenges for estimating 60 pose. First, the severe occlusions often exist, and especially in robotic manipulation, this could happen in the clutter or could be introduced by the hand or arm. Again, let's take a look at the OpenAI dexter hand as an example. So when the hand is manipulating the objects within the hand, there are many cases when the finger is occluding the cuboid. And also, for 60 pose, collecting and labeling ground truth 60 pose data is more troublesome than the 2D tasks. On the bottom right, I showed an example of from the annotation tool. So typical pipeline for annotating 60 pose is that the annotator will drag the marker to make the CAD model aligned with the observed 3D point cloud. And to make sure a high quality annotation is usually required for the annotator to rotate the 3D visualizer to different viewing angles to make sure that this marker is perfectly aligned with the observed point cloud. And this process is really troublesome compared with 2D. In 2D, you just annotate the 2D bounding boxes or semantic segmentations, for example, in the 2D image, and that's it. And also, another problem is that the solution space of the pose is in the SE3 space. And this is more complex than the Euclidean space. So especially for the rotation, it's more tricky. It's in the SO3 space. And that's why there are a lot of literatures studying what kind of representation for the rotation is most effective. Also, last but not the least, the robot will usually interact with the environment actively. So this involves a lot of dynamic process. So faster post-estimation is required for real-time purpose. First, I would like to introduce our recent work published in IROS 2020, AC3 TrackNet, data-driven 6D pose tracking by calibrating image residuals in synthetic domains. The motivation is as follows. So 6D poses of objects can assist and inform control and planning during the robotic manipulation. Consider the example in the right. When the vacuum pick the object and hand over to the right gripper, and then we want to place this object in a constrained space. Throughout this whole process, we want to have knowledge of the 6D pose. And again, this is a dynamic process. We always want the updated pose in every frame. And in many examples, the slippage will happen during the manipulation, especially for in-hand manipulation and human-robot interaction. And also, maybe the case in the right when the handover happens, where the forward kinematics, purely relying on the forward kinematics to extrapolate the 6D pose is not very reliable. And for this reason, a very straightforward idea is to exhaustively apply the single image-based 6D pose estimation methods to every frame along the video. And here's an example on the bottom right. This is a very typical work, post-CNN, and this is what will happen if we exhaustively apply the single image-based pose estimation on every frame of the video. So the problems are very clear. First, the shortcoming is that it's usually very slow for real-time estimation. In this case, this algorithm runs 10.6 seconds per frame, and this is totally not feasible for real-time performance. Another issue is that we can see the estimated pose is actually jumping a lot between the neighboring frames. And this is because this single image-based estimation method does not take into account the temporal consistency. Another issue is that it's usually challenged by significant occlusions, and this algorithm, many single image pose estimation algorithms will suffer from these occlusions since they didn't take advantage of the prior information in the earlier frames of the video. So for all these reasons, fast and accurate 6D pose tracking approaches are highly desirable. For 6D pose tracking, there are some related work. For example, the probabilistic filtering and also optimization-based methods such as the SimTrack. And also recently there are some deep neural network-based approaches such as the DeepIM. However, all these approaches suffer from some major problems. First, it could be computational heavy because in the tracking, especially in the probabilistic filtering like approach, they usually sample a lot of particles and they have to rely on the parallel computation for the to do the heavy computation. It also may fail in the long-term tracking, which means the tracking may get lost, and then you need to reinitialize from the single-based estimation methods. And we can see more examples of the failures in the experiments. Also, for the neural network-based approaches, a problem is that it will usually require real data for training. The DeepIM work, in this case, for example, it will need the real data for fine-tuning. Also, actually, this real data is a very common problem nowadays for the deep learning-based approaches. Collecting and labeling real data, especially in robotics, is not very safe and also not very time efficient. And the contributions of this work can be summarized as follows. Develop the novel end-to-end neural network architecture to track the 6D object pose. And as mentioned before, learning on the real data is not very convenient. So we want to design the framework which only needs the syntactic data for training. And part of the key components is that the smart feature encoding disentanglement enables more efficient sim to real transfer. Also, the rotation is in SO3 space, which is more tricky. Instead of directly regressing the rotation matrix, we choose to use the Lie algebra representation of the 3D orientations, given it has been shown success for predicting the residual rotation in the Lie algebra space. Also, we propose the training pipeline over synthetic data that employs the idea of physically plausible domain randomization for pose tracking. And this can dramatically reduce the manual efforts in collecting and labeling videos for tracking 60 poses. Without this, to learn this tracking of video, it will be a tremendous amount of work to label the 60 poses in every frame of the video. Also, finally, we developed a novel benchmark dataset for 60 pose tracking in the context of multiple different robotics manipulation tasks, since there is no previous existing suitable dataset for this. The problem statement is as follows. The input contains the CAD model of the target object to track, and also the RGB-D sequence containing the target object to track. And our goal is to track the 60 pose of the target object in each frame. Here is the framework overview. Suppose we have some pose in the previous timestamp denoted as epsilon t-1, and this could be either initial pose or the pose estimation from your previous timestamp. And also, because we have the CAD model, we can use the CAD model and this epsilon t-1 to render an RGB-D data denoted as RT-1. Also, at the current timestamp, we have the real observation of the RGB-D data denoted as OT. We send these two inputs, RT-1 and OT, to the AC3 TrackNet, and it will predict a delta transform denoted as delta epsilon t. Then we can augment this delta transform on top of the previous estimate. And this brings us the transformation estimate at the current timestamp. Then we apply the same idea again. Now the epsilon t will serve as the previous timestamp in the next frame. And we have the newly coming images. We do this same process, and we now have the epsilon t+1 for the next timestamp. We apply this repeatedly, and this will bring us the pose estimation for each frame of the video. So the key design is how do we design the network for predicting this residual delta transform. Here's the corresponding neural network design. Our neural network is based on Simon's type network, where there are two branches for the input. The first branch, which is branch A, takes the rendered image from the previous timestamp. The lower branch, which is branch B, takes the real observed image at the current timestamp. Then the pose estimation parameterized by the neural network will take the two encoded features and compare them to predict the residual translation and rotation. Here, the translation and rotations are disentangled for prediction, and the rotations are represented in the Lie algebra space, which is the twist in the manifold. Later, we recover this rotation by applying the exponential mapping to the twist, and finally, it brings us the delta t in the Lie group space. Since our work is only using the synthetic data for training, so there are some key differences between the training stage and testing stage. So here is the training stage. We can see that the branch A takes the rendered image data, and here we should note that the rendered image does not have any background. It's purely the object. The branch B is the current timestamp, and in the training stage, because we are training on the synthetic data, we are generating a lot of photorealistic images, and this is the branch B at the current timestamp. However, during the test stage, the difference is that now we are testing on the real observed data, and by this feature disentanglement, we can see what happens is that The only difference between the training stage and testing stage is the branch B. So in this case, by this feature encoder disentanglement, the domain shift only exists in the branch B, and only the encoder phi B is responsible for capturing the domain invariant features, while phi is always capturing the synthetic, only need to care about the synthetic domain features, both in the training and the testing. And here are some synthetic training data generation examples. In this work, we employed the idea of domain randomization and physically plausible rendering. So we are not only considering to randomize the textures, but also to make sure the objects are naturally lying on the table without collisions. Here are some qualitative results on the YCB-Video dataset. This is one of the two benchmarks that we are evaluating in this work. And here we are compared with the 3 different approaches. The first two are published in AIRLab and Encoder, and they are probabilistic-based filtering approach. Post-RBPF is a recent work published in RSS, which combines the particle filtering with the neural network. And here is one example video on the YCB-Video dataset. So the poles are initialized from the ground truth, and the background are rendered in gray. The estimated objects are rendered in color, overlaid on the gray image. So ideally, the rendered color should be the same as the observed image, and means the post estimation is accurate. You can see that for some traditional probabilistic filtering-based approach, they are struggling to when the occlusion happens. And even when the post-RBPF, the recent work combining the particle filtering with the neural network, is struggling with the textureless object woodblock, whereas the AC3 TrackNet is able to estimate the pose stably. Another key thing to note is that in the probabilistic filtering approach, it is tricky to design a suitable likelihood estimation function. And this work is based on depth, so it's not able to make the texture align with the real texture. So it's only based on reasoning about the depth data, whereas AC3 TrackNet is able to implicitly capture both the RGB and depth modality. And here's one interesting video that we found when doing the experiments, that AC3 TrackNet is robust to complete occlusions, and no reinitialization is required for this video. So in this example, we're trying to track the tomato can, and we can see that along this video, at some point, the tomato can will be occluded by the yellow mustard bottle in the front completely. Whereas the AC3 TrackNet is able to keep track even when complete occlusion happens without suffering from tracking loss. So no post-reinitialization is required. Actually, in practice, for real robotic manipulation scenarios, post-reinitialization is a very expensive operation, because usually post-estimation is slow. And when the tracking gets lost, then you need to do an expensive operation to reinitialize the post, and that may interrupt all your planning or control components. So ideally, without tracking loss, it is better for also the planning and control components for the robot as a whole system. And here are some quantitative results on the YCB-Video benchmark. Currently, the AC3 TrackNet is able to achieve the state of art on this benchmark in both the ADD and ADDS metric. And notice that we are also the method that only use the synthetic data for training, while there are some approaches using both the real and the synthetic data for training. So DOPE is one work that is also using the synthetic data for training, but it also suffers from a large domain gap. So we can see that the results are poor in some categories. Some numbers are using slash here because they didn't report the results on these categories. And other than the performance, SC3 TrackNet is also able to run pretty fast. It can run up to 90 Hertz, whereas the common camera frequency is about 20 to 30 Hertz. So this is far more sufficient than real-time purpose. And here's a plot of the performance with respect to the speed. The y-axis is the performance. In YCB benchmark, the evaluation metrics are usually ADD and ADDS, two different metrics. And the x-axis is the computation time. You can see that the SC3 TrackNet, noted as the star in this case, is able to run not only able to get better performance, but also significantly faster than the alternatives. And previously, we evaluated on the YCB-Video benchmark. The scenario is that the objects are statically placed on the table, but the camera is moving around. And to entirely reflect the attributes of a tracking algorithm, we're also interested in evaluating the cases when the object is moving in front of a static camera. And that is also often the case in the robotic manipulation scenarios. So for this reason, and also because of the lack of a suitable data set, we developed this YCBINEOAT data set in this work. And here is our experimental setup. We use a dual-arm robot, and for the sake of evaluating all kinds of scenarios, we are using 3 different manipulators: a vacuum gripper, robotic gripper, and a Yale hand, adaptive hand. And also, we chose the 5 objects from the YCB-Video benchmark because of their widely accessibility and suitable for benchmarking. Here are some desired properties of the dataset. You can find more details on my paper or the GitHub project page. Here is a qualitative results on the YCBINEOAT dataset. Something to notice is that the tracking is initialized from the ground truth pose at the first frame. Then no reinitialization is allowed. And the rendered object using the estimated pose is masked as blue and overlaid on the grayscale background image. So again, ideally the mask should be perfectly aligned with the real master photo in this case. Okay, now let's look at the tracking process. So we can see that RGF loses the tracking at the very beginning of the video because of the sudden motion when the object is initially picked by the vacuum. Then in this data set, it's kind of challenging because the motion of the arm is very sudden, and there are some extreme flipping of the object. Also, the object later will expose its textureless face in front of the camera. And we can see that for the compared approach, it will suffer from some unstable tracking when that abrupt motion happens. Whereas the SC3 TrackNet is always able to output a stable and accurate tracking until the end. And another thing to note is that we're not using any fluid kinematics. So fluid kinematics, in this case, it may be reliable because there's no slippage of the object relative to the hand. And also, it's only using one robotic arm. But no, in this case, the handover will also make the fluid kinematic not reliable because the object will move with grasp. Here's another example, which is about human-robot interaction. And in this case, the fluid kinematics alone can clearly not perform the tracking. So here the arm is first picking the box. And later when the robot hand over the box to the human's arm will move very quickly, and it's very challenging for tracking. Also, a very extreme flipping happens, we can see that the comparative approach will suffer from the tracking loss, while the SC3 checknet is able to track until the end. And to summarize, SC3 checknet is fast, robust, accurate, and only needs a synthetic data for training. However, there are some remaining problems to address. So in the following, I'm going to first try to answer the question: what if we want to manipulate novel instances without CAD models? And this problem, in the following paper, we are trying to address this question: task-driven perception and manipulation for constrained placement of unknown objects. This is a recent work published in RAL and IROS. The problem we are considering here is that we want to pick an unknown object and place it in a constrained space. Oh, sorry. Feel free to interrupt me if you have any questions.
Yeah, I do have a question. I was just wondering if you've arranged this so that we might have some time afterward to go back to ask questions on the previous paper, or if we should ask those now.
Yeah, maybe it's better if you ask questions for the previous paper right now, because later you may forget your question.
Yeah. Okay. Can I start that then?
Yeah.
I was wondering about the if you go back to the slide that you showed the architecture of your learned, your training system. Yeah, the one that's yeah. I wondered if you could give us a little bit of insight about if you've thought much about the explainability of this, because one of the things that comes to mind for me is it might be useful to be tracking the velocity, estimating the velocity of objects while you're doing this. And I'm not sure if if that's happening, or if you've designed this in a way that you're taking advantage of velocity information.
Yeah, first I think that is a great idea. So for this network, I think although it's not totally the same, but this network is implicitly considering the velocity case, because we are predicting a residual translation and a residual rotation rather than to directly regress a pulse at the current time frame. So so suppose we want the network to basically learn to learn the difference between the two images, and to learn their residual pulse. And so in this case, let's say the delta t timestamp between the two images is always the unit 1. Then this residual pulse is actually the velocity divided by the unit delta t. And another thing is that we are representing this residual in the twist manifold space. So the rotation is already in the like tangential space, and that's why we are applying this exponential mapping to recover this twist into its original rotation space. And then we applied this delta transform on top of the previous estimated pulse to get the current time estimated pulse. So that is like using a velocity and multiplied by a unit timestamp.
Sure. Yeah, I could see those connections to the velocity. I just wasn't sure if there was any explicit attempt to try to like use a smooth velocity.
We didn't explicitly model like strictly using a time to measure the two different timestamps, and then use some translation to divide by that time to calculate the velocity. We didn't to model that.
Okay. If I can add something here, one benefit of just focusing on this delta t is that, let's say that you've in the previous frame you deviated and there was an error, and you overshot in a specific direction. Now you're going to correct it in this delta t without kind of having the bias from that error. Because and you can bring back if your current observation is clean. we discussed with Bowen what about putting, the same setup that he has perhaps in a Bayesian framework where you have like this transition model and you're making assumptions about some smoothness in the velocity over multiple frames. And then, I think it may work. It may be, again, the classical trade-off here is your last observation more accurate than your assumption that perhaps there is some smoothness over time? And if there is a way to also get the confidence of the current observation, perhaps you could be biasing more towards this. And if not, then you could be biasing more towards maintaining like, perhaps an assumption about smooth velocity and then fall back to that, especially when you don't see the objects for some frames.
Right. All right. Okay. Thanks.
Yeah. For this, we didn't model the uncertainty, and we are only using the it's like an optimization approach where we only predict the optimal and trust it. And theoretically, maybe we could model the uncertainty and sample multiple different previous estimate around the unimodal the previous estimate, and then to predict multiple different residual poles with the uncertainties, and then to adopt into something like a particle filtering based framework. The thing is that before reaching to that level, I already achieved a satisfactory result, so I didn't continue along that direction.
Yeah, he complained that it would make his approach slower too, and he wanted to hit that like 90 frequency rate.
Sounds good.
Yeah, it turns out that even when using purely synthetic data, and we can generate as many synthetic data as we want, and this network is already able to get some satisfactory performance. So maybe that's an extension work later on.
Yeah, you got to go for 1,000 hertz later.
Yeah, thanks for this question.
Thank you.
Can I ask another question related to the first paper? Go to the slide where one slide before you have that good balance thing, the result, when you report the results. Yeah. Yes. So I noticed that there are some categories of the modality type where your accuracy is low, where like 36.45, 40.04, right? Is there any insight as to why certain objects your performance is poorer than other objects? Like if I look at the thread, the initialized from post CNN, post CNN. So are you basically saying that let's assume that we don't initialize from ground truth, we initialize from post CNN, right? So
Yeah.
some category, for example, human 011_human. Did I see it at the right row? Like there are two rows where your ADD value is 36.45 and 40%, and there's another one with 39%. I'm just curious, what extra challenges does this category have that prevent you from getting over 90%, for example?
Yeah, for initializing from post-CNN, we did this additional experiments for fair comparison with post-RBPF because they are initializing from post-CNN. And the thing is that in the post-CNN, there are some videos where the initial post-CNN is wrong. So for example, woodblock will rotate 90 degrees. And in that case, because our SC3 TrackNet is comparing not only the depth but also the texture information, and the post RBPF is more like reasoning about the depth information. So when let's consider the wood block. So if the wood block rotates 90 degrees, then the SC3 TrackNet will get confused, and it will predict some non-reasonable poles.
Okay. All right. All right. Thanks.
Yeah.
Bowen, I had one last question about this. When you're doing this, you're doing it at 90 hertz, but when you get data from a camera, or most cameras, they won't work at that frame rate. So what do you think will be the performance drop, or is there a performance drop when you might not get all the frames and the velocity of the robot, of the objects might be larger? So for instance, you don't get a smooth transition between the, let's say, initial pose to the final pose of a object.
I forgot to mention this. So this 90 hertz is to measuring the running time of the approach. But actually, when evaluating all these data sets, the images are collected using the camera with the 20 to 30 hertz. So, like when the frequency drops.
Okay, I see.
Question that when the frequency drops, the difference between the two images will be bigger. The thing is here that we are actually evaluating on this camera's frequency. And this 90 hertz is to only measure the running time of this. So in real practice, we're still using the TrackNet to track the 20 to 30 hertz cameras capture the images.
Thank you.
Yeah. Any other questions for this first?
Can I ask a question at the same page?
Yeah.
Sorry, small question. Yeah. All right, thank you. So I see that. So how do you measure the frequency from the previous approach? So did you get it from their data, or did you run it on your local machine? So for the reference 2, 3, and 1. Yeah.
2, 3,
and 1. For the reference 1, 2, 3. You got frequencies for 5, 12 hertz.
For 2 and 3, we were evaluating on the same machine.
Oh, right. Yeah. That will answer the question.
Because 2 and 3, they released their code.
Yeah, like very long time ago. Right?
Yeah.
Okay, I see.
Yeah. Any other questions?
No.
Okay.
We can move forward.
Yeah. Go ahead.
No, you can continue on your presentation.
Okay. Yeah. Now let me talk about the task-driven perception and manipulation for constraint placement of unknown objects. So the problem we're considering is that we want to put the unknown object and place it in the constrained space. So for the unknown object, we have no prior about the object CAD model or category. And for the constrained space placement, it requires informed picks and regrasps. So the motivation is that first, why we choose to not reconstruct the object models. The reasons are it's time consuming and often requires costly setup. Also, the object shapes can vary significantly between different instances within object category. So when we even when we reconstruct the model of this instance, next time when we manipulate another instance, the reconstructed shape may not be applicable. Also, precise or complete models are not always required to complete a manipulation task. And why do we need manipulation planning? Because only some picks will allow the constrained placement due to the reachability constraints. And planning actions ahead can provide better solutions, such as avoiding regrasping. So to this end, we propose an integrated perception motion manipulation planning framework for pick and constrained placement of unknown objects. For the object representation, in front of the camera's view, there are two categories. One is the unobserved regions, which is outlined in the red, and the other is the observed space, which is outlined in the green. And this part is a visible part in front of the frustum by the camera sensor. And then the object is represented simultaneously by two different forms, the conservative and the optimistic estimate. For the conservative estimate, it's computed by using the by considering the unobserved part as well. So this ensures the computed actions are safe to execute because the collision checking are based on a larger, more conservative estimate. The optimistic estimate is only considering the observed part, and it will guide the action selection when the conservative planning fails. And also, when the manipulator is moving the object in front of the camera, when we have additional viewpoints, the estimates will be dynamically updated. Here is the overall manipulation planning framework. So first, we will check if the manipulation can already be achieved by reasoning the conservative estimate. If the solution is already able to be found, then we just directly execute this plan without any further update. Okay, now in some cases when the conservative estimate is not able to bring us any solution, then the optimistic planning will guide the peak and will update the object estimate. For example, in this case, we will update the conservative box outlined in green. And then when the object is updated at some point, even with the conservative estimate, the solution is able to found, we just execute the plan. Here is our experimental setup. In this case, we are using the robot with two manipulators. And for different kinds of objects, they are initially placed on the top. And the goal is to place the objects in the constrained space. Here are some results. Here are some quantitative results. So in this work, we conducted 120 experiments with 5 different objects. And with the proposed framework, by integrating perception and planning, we're able to achieve the highest success rate compared with other baselines. And here's the quantitative results in terms of the efficiency of the manipulation. And you can see the framework reduces both the motion time as well as the number of sensing actions so that we can achieve a more efficient manipulation without shape priors of the objects. Okay, so any questions for this paper?
Hi, Bowen. Because you are trying to manipulate novel objects, so
Yeah.
what if the object cannot be represented by a bounding box? For example, if it's a nut, or it's another weird shaped object. So can your method still work?
So actually here we are, it's not strictly a bounding box, it's actually a voxels inside a box. So let's say if there is a slope formed by this frustum, then the voxels under this slope will be represented as unobserved. So for the voxel representation, there are 3 types. One is the empty, which means any regions except the red or green in this case will where we say there's no voxel occupied in the object's frame. The other is it will certainly be occupied for those voxels which are under the observed, which are under the observed box. Those voxels are certainly occupied. And for other regions, for the ones that is under the unobserved regions, those voxels are marked as uncertain. And for the conservative estimate, it's a union between the uncertain voxels with the certainly occupied voxels. For the optimistic estimate, it's only the certainly occupied voxels. So for some weird geometry shaped like objects, for example, the knives or scissors, then the voxels will be able to depict the general contour of the object. And by changing the resolution of the voxel, we can trade off between the efficiency and the detail level of the representation.
Thank you.
And for the ease of the collision check, we can use the bounding box for the collision check, or we can use the voxel for the collision check. And the rest of the manipulation is the same. So if the conservative estimate is already able to bring us a plan to place the object, then we just go ahead to place. Otherwise, we will try to update until we can find with the conservative estimate.
Thank you.
Yeah, no problem.
Well, just to follow up on Linda's question, what happens if your object has holes or it's really non-convex? So for instance, if you have a cup with a handle, will this representation capture the fact that there's a hole in the object, or is it just going to be a local convexification of that?
Yeah, that's a very good question. So in this work, the manipulated object doesn't have those those kind of topology, and I guess by the voxel, like in some cases it may be able, but we didn't do experiments on that.
Thank you.
Yes, thank you. Any other questions? Okay. Then I will go ahead with the next pose. So the second remaining problem is that how do we initialize a pose for tracking during the dexterous manipulation when the objects are occluded by the adaptive hands? And this paper, robust occlusion wheel pose estimation for objects grasped by adaptive hands, will try to answer this question, which is published in ICRA 2020. So there are many related work in single image based 6D pose estimation. And a common similarity between them is that they're mostly focusing on tabletop static scenarios. However, in the robotics community, especially for robotic manipulation, there are many cases when the objects are not lying on the table. For example, during the manipulation, let's say if the tracking is lost, then what will be due to reinitialize the pose? And the problem we're considering is that given the input RGB-D data, when the object is held by the hand and the severe occlusion happens. Also, suppose we have the CAD model of the object and also the URDF of the adaptive hand. We try to estimate the hand and the object pose. And one thing to note is that we are considering the adaptive hands where the forward kinematics of the fingers are not necessarily available. For example, the yellow adaptive hand in this case, there's no forward kinematics, and the forward kinematics is only up to the wrist. So we also need to estimate the fingers configuration. The contribution is summarized as follows. This is the first purely vision-based robotic hand object pose estimation framework that takes into account the fingers pose change. In previous work, there are some approaches which assume that the objects pose doesn't change after grasping, and they will just use the pose when it was grasped. But this is not necessarily true, especially for in-hand dexterous manipulation. Also, many pose animation are using the tactile sensing to assist the tracking, to assist the pose animation because of the severe occlusions. But the tactile sensing is not always available, and also it will introduce cost. So we are interested in exploring by using only camera if we can solve this problem. And it also has some desired properties of high precision, computational efficiency, and robustness, which will be shown in the experiments. And because of the lack of a suitable data set, we also developed the first robotic hand object estimation benchmark, including the synthetic and real-world annotated data. So first, we try to address the problem of the hand pose so as to approach the object pose estimation. Because of the forward kinematics or the camera calibration error, we first apply ICP between the observed point cloud and the CAD model by using the forward kinematics until the hand raise. Then we deploy the particle swarm optimization parallel search for the optimal finger configuration. The objective function is defined by the matching score between the hypothesized finger configuration between the and the observed point cloud. But the hypothesis is subject to two constraints: the collision constraints between the two fingers and the motion constraints defined by the URDF. Once we have the hand state estimation, we are able to generate the 3D significant field around the hand. And this is utilized for three different purposes. First, it's able to prune the point cloud segment corresponding to the hand. Second, it's able to generate heuristics for efficient object pose hypothesis generation. And third, it can help us to do efficient collision checking to prune the false positive pose hypothesis. First, let's look at for pruning the object, pruning the point cloud corresponding to the hand. Let's say we have the raw point cloud. There are two different views. Once we have the hand state estimation, we can eliminate the points which are very close to the hand mesh. And here's the remaining point cloud, which we assume to belong to the object. And of course, there are some outliers which may not necessarily belong to the object due to the sensor's noise. And the remaining task is to solve the object pose from this object cloud segment. And the second functionality of the significant fields is that we can build a simple probabilistic model to model the likelihood of every point belonging to an object. In this case, we are using a simple exponential distribution. And here is a heat map depicting the distribution of the probability distributions. So intuitively, the points which are further away from the finger's surface are more likely to belong to the object. Once we have this probability distribution, it can used for heuristics-guided pose hypothesis sampling. And here's the sampling process. A brief introduction about the sampling and the registration. So here we're using the Super 4 PCS registration. And the basic idea is to sample 4 coplanar points on one point cloud, and then find 4 coplanar congruent sets in the other point cloud. And in this case, it's the CAD model. These congruent sets can be efficiently found by building an oak tree from the CAD model. Once we have this correspondence, we can solve the pose in the closed form. And this is one example hypothesis. We can find other pose hypotheses using the same idea. And once we sample one set of 4 coplanar points, we can decay their distribution so as to encourage the exploration on other unexplored areas. So here is an updated distribution. And using the same strategy to find the false hypotheses. We repeat this process until we find enough false hypotheses. Now there are many false hypotheses, and many of them are false positives. The remaining part, we are using this Sanderson field to prune those false positives. The rejection could be due to the collision or some objects floating in the air. Also, the depth data is actually 2.5D. So we use the hypothesized pose to render the object and compare the rendered depth versus the observed depth. Finally, we select the false hypothesis with the largest common point size score. Yeah, here is the final estimated pose. And in the following, let's look at some qualitative results. In this case, we are comparing two different approaches. One is the Super4 PCS, which is a registration-based approach. The other is the AE, which is a deep neural network-based approach published in ECCV 2018. And because there are no prior works that consider the robotic hand with the object pose, so for fair comparison, we augment both approaches with our hand state estimation component, and also augment them with the ICP for refinement. And here we are trying to estimate the pose of the ellipse being held in the hand. In this case, the majority of the ellipse is being hidden by the finger, and our approach is able to solve the pose. Here's another example using the object from TLAS dataset. And the lighting conditions here is tricky. Also, the major part of the object is occluded. Okay, finally, let me briefly talk about our ongoing work towards generic rigid 60 object pose tracking for manipulation in the wild. So compared with prior work AC3 TrackNet, there's no need for CAD model. And also, in contrast to REL work, there's no need for fluid kinematics or deliberated planning to assist the tracking. And it can enable manipulation in the wild without shape priors. Also, because it does not rely on any assumption on the kinematics, it can do tracking in the wild, including human-robot interaction or various scenarios. This is the work in the preparation for submission to April 2021. And due to the time limit, I'm not able to cover all the details. And you can always find more details on my web pages. Also, the code of the first and the third work are already released. For the second work, I haven't checked with the leading author whether he plans to release or not. And the videos can also be found on my web page. Also, I would like to thank my collaborators, my advisor, Professor Kostas Bagris, Chantaya, Professor Bolarius, Andrew, Avisha, and Baozhang. Also, I would like to thank you for inviting me for this talk. And feel free to let me know if you have any questions. Yes, thank you.
Thank you.
Question.
So student and other faculty, anyone have any more questions for Bowen?
I had a quick question about the last paper.
Sure.
So for all the examples that you use, you essentially have objects that are able to be completely surrounded by the two graspers. But what about objects that have like a knob or something like that? Does the algorithm often recognize the object as the grasper? And what would happen in that case?
Sorry, you mean the objects that have what?
So all the objects that you've tested with can fit completely inside of your grasp, essentially. What if they can't?
Yeah. Fit into the grasp. Oh, you mean when the hand is not able to grasp the object?
No, sorry. I mean, like when so in all the cases, the graspers are able to completely surround the object. So essentially segmenting the grasper itself is pretty easy. But what about the case where you can't as easily segment the grasper, like the object in the grasper may be ambiguous?
Sorry, I'm not sure if you understand. You mean, for example, when the object is outside of the finger?
Yeah, like the object is too large to be completely encompassed inside the
Oh,
grasp.
yeah. In that case, actually, in the objects we are considering there are some cases when the object which is not strictly like horizontally between the fingers plane, and actually, because we are building the signed distance field in the 3D space, so after pruning the hand-related point cloud, the probability distribution will still reason about the 3D distance. It's not only about the 3D distance from the finger. So when let's say when the object is outside of the plane, and it's let's say it's extruding in the z-axis, then the distribution will reason about that. And when we sample the pose hypothesis, it should be able to cover that.
Okay, thank you.
Yeah, thank you.
Hi, Wenbo. Thank you for the presentation. I have a very basic question. When you have this point cloud, I'm imagining that you're using camera to photo or see the scene first. How do you take the camera and then generate the point cloud?
The camera, you mean where is the camera mounted?
No, if you take the camera input, how do you generate the point cloud? Is there any?
Actually, this is the RGB-D camera. So we can, so we have the image and we have the depth of each pixel. We can convert the RGB-D data into the point cloud.
And what is the library that you use to convert it?
Actually, I have released the code. I didn't use the library. It's part of in the code base. I wrote this function myself. You can,
okay.
Yeah, you can reach me offline, and I will point you to the link.
Okay. Good. Thank you.
Yeah, no problem.
Because we don't have access to the slides, can you actually type the code GitHub link in the chat?
Oh yeah. Yeah, sure. Let me
just copy it into the chat.
Okay.
While Bowen is doing this, let me take 1 minute to advertise a new program that is starting at Rutgers University. We received recently support from the National Science Foundation to start an NRT project and an NSF research training program on what we call socially cognizant robotics. And it's collaboration among 10 faculty at Rutgers, computer scientists, electrical engineering, mechanical engineering on the technology side, as well as cognitive scientists from psychology and public policy researchers from the social sciences. And the program provides fellowships for US citizens and green card holders to be supported for graduate studies and also new courses in this area, kind of interdisciplinary between the technology side and the social and cognitive sciences that are open to everyone. So if you have interested students, perhaps, you know, undergraduates at Lehigh that you may have joined a group that are thinking of going to graduate school, please encourage them to reach out to us for this new program. It's very exciting and it's highly interdisciplinary.
Okay, thank you both. So
Thank
is
you.
there any more questions? So if not, let's thank Bowen for this excellent talk.
All right, thank you, Bowen.
Thank you.
And hopefully in the future we can, you know, host you physically in the Lehigh campus.
Yeah, sure.
Welcome to anytime when the COVID is over, you can come and visit us.
Yeah, sure. Sounds great.
All right. Thank you very much.
Yeah, thank you.
Bye.
Bye.
Bye.